Hello students, welcome to SB Math Stat Physics class. Today we will proceed to binary relation episode 2. Binary relation episode 2. So without wasting any more time, let us enter into this episode. First, we will learn what is called inverse of a binary relation. Let R be a binary relation from a set A to a set B. So A and B are two sets. So this means that R is a non-empty, R is a subset of A cross B. The inverse of this binary relation R, denoted by R power minus 1, R to the power minus 1 is the notation for the inverse of the relation R. This relation is from the set B to the set A. And how it is defined? This is defined as a set AB. Okay, so you can rather write BA. Okay, so where BA comes from which set? BA comes from B cross A set. So this is the first condition about the element of R power minus 1. But there is one more condition, and AB belongs to R. Okay, so R inverse is this set. So we can say in other word, we can say that if A or B, then B or inverse A. Okay, so if A has R relation with B, then B has R inverse relation with A. Or if you find that U R inverse V, this means that V or U. Okay, now we will learn composition of two binary relations. Let R be a relation from the set A to the set B, into the set B. R is a binary relation from the set A into the set B. The proposition we use is into. So R is a binary relation from the set A into the set B. And SB, a binary relation from the set B to the set C. Remember, these two sets are same. So S is a binary relation from the set B to C. Then we can define a binary relation from the set A into the set C obtained by composing these two binary relation, and that is denoted by S, put this sign small o, and R. So this is the symbol for the composition of the mapping of the binary relations R and S, and this binary relation is defined from the set A into the set C. And how this binary relation is defined? If you say that X comma Y belongs to SOR, then this means that you can find, so this is the symbol of you can find or there exists. If there exists, or if you can find an element, say name it U, belongs to B such that XU belongs to R and UY belongs to S. Okay. So do you understand? So if you say that XY belongs to SOR, or in other words, if you say that X has SOR relation with Y, then this means that you can find an element U in B such that X has R relation with U and U has S relation with Y. Okay, so in other words, or in set theoretic notation, SOR is the set, SOR is the set whose elements are of the form XY. And what are the conditions to be satisfied for this element? XY should belong to A cross C. Remember, SOR is a relation from the set A into the set C. So XY belong to A cross C, and what? And there exist U belongs to B such that XU belongs to R and UY belongs to S. Okay. Now let us take an example. Let us take three sets A, B and C. Let A be A, B, C, D, and let the set B be X, Y, Z, T, and let the set C be P, Q, R, S. Okay? Or just take three elements. There is no need to take every element, number of every elements of the set to be equal. Okay? You can change the set B. You can take 3 elements, 2 elements, or you can take even 5, 6, whatever you want to take. And let lambda be a relation from the set A into the set B, and this be given by AX, AZ, by, bz, bt, and take ct. Okay, and let mu be a relation from the set B into the set C, and let it be given by xp xr yq tr, and let one more element zp. Okay. Now the first question is, what is lambda inverse? That is lambda to the power minus 1. As I have told you in the definition, is very easy. Lambda to the power minus 1 is a binary relation from the set B to A, and the elements of lambda inverse is XA, ZA, YB, ZB, TB, TC. Okay. So what is lambda inverse? So lambda inverse, this is a binary relation from the set B into the set A. And how lambda inverse will be given? This is XA, ZA, YB, ZB, TB, TC. Clear? So I think you can yourself write mu inverse. Okay. But now I pose the question like this. You have to find mu o lambda, that is composition of two binary relations. So now this relation is defined from the set A to the set C, and how mu o lambda will be defined. So mu o lambda will be, suppose if you write A, then it is x. Here you have x comma p, so you can write AP. But AX and XR, so you can also write AR. Okay. So x, there is no more x. So AX is exhausted. Now there is AZ, but there is ZP, so you can write AP. Okay. There is BY, BY and YQ, so you can write BQ. Okay, so there is any more Y? No. Now there is BZ and there is ZP, so you can write BP. Okay, so there is no Z. Now here you have BT and you have TR, so you can write BR. Okay, you have CT and you have TR, so you can write CR. And any more element? No. So this is mu o lambda. So this is the relation mu o lambda, which is defined from the set A into the set C. We have defined mu o lambda, composition of two binary relations, and it is from the set A into the set C. Can you define lambda o mu? Can you define lambda o mu? Remember, if you want to define lambda o mu, so mu is lambda is a relation from the set A to B, and mu is a relation from the set B to the set C. So for lambda O mu to be defined, you must have these two sets to be equal. But since A and C are different sets, so lambda O mu cannot be defined. So here lambda O mu can be said to be non-conformable or not conformable. Okay. So for both lambda O mu and mu O lambda to be defined, each of the binary relations lambda and mu must be defined on the same set. On the same set. That means on the set A to the set A itself. Okay. Even then, take examples that lambda O mu and mu O lambda may not be equal. Okay. So now we will take some examples on binary relations on a set